Awesome. Yeah, thank you very much for your kind introduction. Yeah, okay. So just to quickly introduce from kind of a sentence, basically, what Ivy is doing. What we're trying to do is essentially unify, yeah, all the machine learning frameworks, which is quite a grandiose, ambitious thing. At the moment, we support JAX, TensorFlow, MXNet, PyTorch, and NumPy. But we've designed things such that long term we can scale to many more frameworks in the future and so on. So that's kind of what we're doing in a nutshell. Also, actually, just before going on to the next slide, I just want to say, particularly with there's not being a huge group as well, if anyone has any questions as we're going through, then please feel free to ask in the process, because I am a big believer that, yeah, like if half the people in the room lose me somewhere, then it's very good, obviously, if I can then clarify things. So by all means, feel free to jump in at any point if you want me to explain something a bit better. Okay, so Ivy essentially enables two things, two like slightly different things. So it enables automatic code conversions between frameworks, and as well as that, it is also an ML framework in and of itself with multi-framework support. And these two things have slightly different motivations, but there's a strong overlap, and a lot of the work is kind of conducive to both of these. So to start with, let's just go through the motivation. So basically, the last few years has seen quite an explosion in machine learning and particularly deep learning. And what this is showing is the number of GitHub repositories containing the term deep learning over time. I've not updated it since I made this kind of end of 2020, but I'm assuming that the trend continues. And yeah, this is a wonderful thing for researchers and developers. But when we also consider the speed at which these frameworks are evolving, the shareability of code is significantly hindered, and projects and libraries can become outdated in a matter of months if not rigorously maintained against the newest frameworks and also the newest framework versions. This is kind of the setting that we're trying to solve. So if our desire is to provide a new framework which simultaneously supports all of them, we need to find where this common ground lies. And when searching for the common ground, the first thing we can see is that Python has become a clear frontrunner. And then when we look a little bit deeper, we can see that all of these frameworks follow almost identical core functional APIs, but with unique syntax and arguments. And it would seem that there are only so many ways to manipulate a tensor, and unsurprisingly, these fundamental tensor operations are consistent between frameworks. And broadly, the type of functions that are implemented haven't really changed since NumPy first introduced in 2006. And so a simple and scalable abstraction layer therefore presents itself, which is the functional API of all of these existing machine learning frameworks. And essentially this diagram just here showing that we're currently supporting all these various frameworks. A lot of them, or some of them, have become deprecated, and that Ivy is primed to continue to support future ML frameworks in Python. So just a bit of a word on kind of the setting that we're trying to address. So at the moment, with researchers, but also with companies, there's very much a case where people are encouraged to essentially back a horse with their framework selection. So it might be that actually there's some amazing author code from DeepMind implemented in JAX, but there's an amazing ecosystem in PyTorch with all these amazing libraries, and you kind of end up needing to trade off which you then go for your own research project or your own project in a company. And then you kind of have to limit yourself and close off a lot of doors to other very useful tools and implementations. With Ivy, this can be a thing of the past, and essentially we want to open up the whole world of machine learning tools to everybody simultaneously. And there's going to be no need to choose to back a horse, but actually there's kind of a joint layer that makes everything jointly possible in any project. And just to flesh this out with a particular example, I don't know how many people are into transformers. Whether you are or not, it doesn't matter. Just for this example, there's an architecture recently, or quite recently, called Perceiver.io from DeepMind. And this is, quite a popular architecture that can do some general computation. And what happens in the moment is when a paper comes out, a lot of open source developers kind of rush to re-implement this code in all machine learning frameworks. And this leads to many different versions. And I've just taken a few here for Perceive IO, all of which have some traction and have some users and getting attention. But obviously what inevitably happens, particularly in machine learning, very much the devil is in the detail, really. So basically, maybe some things train well, maybe some have a loss function that's not quite working, maybe something was included in the paper that's not included in one of them, or there's instability and so on. And then there's going to be lots of issues and pull requests to try to address this. And this, again, is just more time invested from developers trying to get things working. And yeah, lots of GitHub users involved in this whole process, trying to get the original results and trying to get things working effectively. And with Ivy, this process that otherwise can involve possibly hundreds of hours and possibly even hundreds of developers, in the extreme case, can essentially be converted into a few seconds, whereby you take the module from the official original implementation, you compile it into Ivy, and then you convert it to any backend you want with a computation graph that's guaranteed to be identical. So this is quite a powerful ability where we can just remove this whole process of re-implementing things, and this will, in our long-term vision, this will be unnecessary entirely. So in that case, we kind of explain this hypothetical situation whereby we can convert an author model with a guaranteed identical computation graph. But going further, essentially what Ivy might be able to provide is, in quotations, an infinite shelf life to code bases, whereby you can write something in Ivy, and we have designed things such that we can scale very easily to future frameworks, provided that they can expose a Python interface to their own functional API, which maybe consists of 150 functions or so. And if they can provide this interface, then all of Ivy's high-level classes and functions and convenience methods and everything, the whole Ivy ecosystem will then support this new framework very quickly. So we've designed Ivy to be future-proof, whereby we're not making strong assumptions about the backend or the devices or anything. We're just kind of abstracting at this functional API layer so that we can be we can adapt very quickly to changes in this still turbulent space. So yeah, future-proofing is another big benefit of Ivy. And again, just to kind of touch on this reinvented wheel analogy I'm using. So just what the setting looks like now is you've got all these different frameworks. They all have their own functional APIs, shown here in gray at the bottom. But they also all have their own classes, and they have their own trainable modules, their own optimizers, and so on. Whereas, yeah, these are all, I would say, again, reinvented wheels to some extent. And what we can do with Ivy is essentially wrap all of these functional APIs, and then we only need to implement any of these classes or optimizers once, and these classes then support all frameworks, current frameworks, and also are primed to support future frameworks very quickly through wrapping into the functional API. So again, just kind of another point here that we're trying to create one wheel to fit them all, rather than reinventing another one. And this then might make you think the following, which would be fair enough. Maybe there's JAX and TensorFlow and PyTorch, and now we're coming in and trying to say, hey, here's what the functional API should look like. Aren't we just going to make the problem worse by adding another standard into the mix? And this is a fair point, and in some areas that this can be a difficulty that standardization follows. But I think one of the most important points to make here is that using Ivy doesn't mandate people using Ivy to then fully adhere to Ivy standards. Effectively, your code can include 1% Ivy, 10% Ivy, or 100% Ivy. And it's fully interchangeable with existing code. So you can just use 3 or 4 Ivy functions in your entire PyTorch code. You can just use Ivy to do the conversions between existing frameworks, or you can write your whole code in Ivy and have this kind of future-proofing and this multi-framework behavior. So unlike ACE charges or other examples referenced here, it's not kind of a competitive standard. It's kind of a very much a complementary one. In addition to that, we also don't want to throw another functional API into the mix to kind of add to the huge number already. So we're working closely with the Consortium for Python Data API Standards, which is a huge effort. Well, it's an effort to standardize all of these array APIs in Python, and it's got backing or some kind of sponsorship or advice or involvement, let's say, has loose involvement from lots of top Python array frameworks or companies. So all of these listed here in the logo are involved in one way or another. The actual team over there is led by Quansight and is involving people who are top contributors to NumPy and Pandas and scikit-learn. And they've done some amazing work in defining this kind of lowest common denominator between the frameworks, such that all existing machine learning frameworks have a realistic path to try to find some common ground and actually make translations easier and reduce fragmentation as much as possible. So we are working very hard right now to adhere to this standard, and we think we'll be the first framework that fully adheres to the standard. And this is also growing, so we very much don't want to be another API, and we should then be fully aligned with the standard. Okay, so just a point to make here is that we're in talks with lots of companies and also open source repositories who are very keen to use Ivy in their own repository. I've got a load of companies listed at the top, and then some repositories. Maybe you recognize some logos, maybe you don't. That's not a problem. But a lot of these repositories have thousands of stars, thousands of users, millions of downloads, and have their own issues with either only supporting one framework or needing to re-implement things. And Ivy has the possibility to make that a lot simpler, and we've had very good conversations with all of these, and they're all very excited for us to add in support when we've got our own roadmap, when we're a bit further along our roadmap. Okay, so now I'll just dive into the design a bit. So the high-level diagram of what we're doing is here. Essentially, I've separated things into three groups. There's the building blocks in orange, which are kind of fundamental to both of these points, which is whether Ivy is seen as a code converter or as a framework in and of itself. So orange are kind of fundamental to both of these. Then purple is enable code converting, and green is then when you're considering Ivy as a fully fledged framework. And again, this is a dependency graph, so arrow from B to A means that B depends on A. And we'll just now go through these for the rest of the talk. I won't go into too much detail in the green, in Ivy as a framework for time, but this is all thoroughly explained in a blog series on Medium, and also you can ask me questions afterwards, and I'm very happy to answer anybody that would like to know more. So let's start with the building blocks, and let's start with the Backend API. So first, simply, for each of the supported backends, we have these stored in separate files, in separate folders. So Ivy functional backends here, this is the NumPy one, this is the MXNet one. And for the case of Clip, this is very simple. It's essentially a syntactic difference, and we just wrap the backend method here. For slightly more complicated functions, again, slightly more complicated, where perhaps the method is not implemented in the backend, then we just need to implement this as a composition. So this would then be tf.linspace and ivy.defaultDevice here, and essentially we can implement logspace by using the linspace and raising it to the right power. So the backend implementations just take whatever functions are available in the backend and wrap this so that we can implement the function in Ivy. And that's essentially it. I mean, this is what the backend APIs look like. They get a bit more complicated than that in some functions, but generally speaking, it's relatively simple to use the existing API to wrap things to support the Ivy API. So now going into the Ivy API, this is what an example function would look like. So this is in a separate folder, and we here define what the method should look like with regards to the input types, with regards to the behavior. So we define that in the doc string. And you notice that previously we don't have doc strings for all of these because we don't need to keep repeating ourselves. It's the same behavior. So we only put all of this in Ivy. In here, for every function, we just return get current framework with the input argument put in, and then we call the backend method, which is an attribute of the backend framework here. So hopefully that makes sense. And yeah, so a point to make now is that we can either infer the backend framework implicitly, or we can provide this explicitly. And this essentially is what this current framework enables. So if you haven't set your framework explicitly, then we just take in the value X, we do some type checking, we work out what framework you're using based on the type. So if it's a torch tensor, we work out that it's torch, and then we call the clip method, which is specific to torch in this case here. And this example here just shows this basically. So in this case, there's no backend framework selected. If we set the framework as torch, then directly ivy.concatenate will call the backend function straight away. If we haven't set it explicitly, we'll actually call this method here directly, and then we'll enter into here, determine the framework, and then return the correct result, which is why these are operating in slightly different ways. But either way, we return a torch tensor. In this case, we still haven't selected the backend, even when we inferred it from the inputs. But in this case, we have explicitly set the framework, so it's listed as the current framework. And that's essentially how the Ivy API and the Backend API interact. I'll then talk a bit about the framework handler and how we can tidily and cleanly set this framework. So this method here, which was current framework, which, just to remind you, was what we have at the bottom of clip and what we have at the bottom of every function in the Ivy API. This basically goes through three processes. So first of all, if we explicitly provide the framework, which we can do in any function such as clip, then essentially we return it straight away. Otherwise, we take a look at the framework stack, which is where we have set the framework globally. So if we call ivy.setFramework torch, then this global framework stack will be updated, and then we return this if the framework wasn't explicitly provided. And then finally, if there's no explicit framework, there's no globally set framework, then we infer the framework from the arguments just using string parsing. So we don't import all of the supported backends to compare. We just parse the string and work out which backend the object has come from. So this is how we can kind of infer the framework implicitly during Ivy functions without having set the framework. And then a quick point on which is important here is how then we actually set the framework. So we don't want to have to import a specific module like import ivy.functional.backends.torch as Ivy. That would not be, it would be okay, but it would mean that our code is not that nicely written, let's say. So what we do is that we enable you to just import Ivy and then call a method ivy.setFramework. And then this will update the global Ivy namespace with all of the backend specific methods. And I don't need to go through every line in loads of detail, but essentially, just in words, we make a copy of the original dict. We set the framework on the stack, and then we iterate through the original dict items. And if the method doesn't exist in the backend module, we add the original Ivy method, and then we update the global Ivy dict with this method. And then maybe we log to the terminal as well. And what this means, just kind of from a high level, again, no need to kind of go through every line necessarily, but what this means in words basically is that we update every Ivy method which also exists in the framework specific backend namespace. But if it doesn't exist in the framework specific space, then we don't update it at all. And this essentially means that the backend APIs form a subset of the full Ivy API. And I'll go in an example in a second, but so for example, we have a method in the Ivy API, which is a function, which is lstm update. And this method is implemented entirely as a composition of other Ivy methods. So we don't need to implement a TensorFlow version and a PyTorch version and a JAX version. We just implement this once purely in Ivy. So there is no backend methods for LSTM update, but there is for concat or matmul, where we essentially directly wrap and we implement these for each backend separately and wrap the associated method. And this is then essentially kind of what this logic's doing, whereby we're only updating the methods in the global namespace that also exist in the framework-specific namespace. Yeah, so this is essentially why the backend APIs are a subset of the full Ivy API. And just, again, we don't need to go through the whole logic of what an LSTM does, but this is then what the LSTM update method looks like, which doesn't have backend implementations. It's just all implemented in Ivy with ivy.reshape, ivy.matmul, ivy.unstack, and so on. So there's no need to kind of duplicate lots of code and re-implement this method 5 times. And there's many other methods where this is the case, and they're slightly higher level where we can implement them as compositions of low level. Okay, so that's kind of how the framework handler sits into this loop. I'll quickly just blast through the Ivy compiler, then I'll maybe stop to see if there's any questions, because I have a tendency to go quite quickly, and I've deliberately given myself a bit of time, so there is time for some questions. But just very quickly, I'll go through the Ivy compiler, then I'll take a quick break. So the Ivy compiler basically, just as this diagram shows, and again, this is a dependency graph. So actually the flow is to go from code to the graph, but the graph depends on the compiler and the compiler depends on code. So essentially we take any code from any machine learning framework, run the graph compiler, and then what we get out is a graph as a composition of essentially the functions in the lowest level in Python. So this would be the functional API. So even if you've used a Torch module, you will get out a graph composing only of functional operations in Torch stitched together in Python. So there's no C++ or anything here. It's purely a Python compiler. So just as a few quick examples, whether we have pure Ivy in the method we're compiling, pure Torch in the method we're compiling, or a mix, in all cases, we compile to the exact same graph, which is a pure Torch graph taking our input and giving us our return. Likewise, if we have a network that does a simple forward pass with a linear layer, or we have a simple function that does the same, or we have a function that has printing and temporary variables that don't actually connect to our output, all of these again compile to the exact same graph, which is just this simple kind of fully connected layer without an activation effectively. So this is what the graph compiler does. It kind of takes whatever function you've got and finds the low-level functions that connect your inputs to your outputs and kind of discards everything else. And just a quick point is that this is the only form of compilation Ivy supports. So what this does is effectively kind of removes all wrapping code or class code or high-level code from your computation graph, but it still essentially operates in Python. What these functions do is bind to the framework-specific compilation functions that compile to a lower-level language, such as TorchScript or using XLA or kind of CUDA and so on. So we still have support for compilation as is done in the backend frameworks. So I've kind of like blitzed through the building blocks there. I would maybe just stop because I certainly would like, hopefully, for people to kind of be following the thread of what I'm talking about. So yeah, I'll quickly pause now in case anyone has any questions, just for a few moments. So, okay. So then we look at how Ivy operates as a code converter. So effectively then what we do, quite simply, is we build on top of Ivy's unified API with framework-specific front-end APIs. So just to quickly revisit, this is what the back-end functions look like, as we already saw for clip, for example. So all these different implementations unified to one syntax and call signature. this is what the Ivy method looks like, where we have the doc string and we define the allowable input types and so on, and we enable implicit framework selection. And then this is what the front ends would look like. And I've deliberately chosen a very simple example here where, again, it's just a syntactic difference. But what we basically do is then wrap Ivy to kind of create the framework-specific method. So we're re-implementing clip by value by wrapping Ivy, or we're re-implementing torch clamp by wrapping Ivy, and so on. And again, obviously, with more complicated functions, we might need to actually implement some of these methods as a composition of Ivy functions. But in this case, it's effectively just name changes. So this is then, as a high level, what we have overall. We have framework-specific backend methods. We have a unified one function accepting all tensor types with a single syntax, single call signature. And then we have framework-specific front ends re-implemented again using Ivy. And what this then gives us is the ability to arbitrarily mix and match front ends and back ends. So you can then, basically what this means is you can take a torch code and run it using Ajax backend. And I'll kind of flesh it out with an example a bit more now. So basically, if we have, for example, one hot, this torch method here, we've implemented this using Ivy, and then in the backend for NumPy, this is what the one hot method looks like. There isn't a one hot torch, there isn't a one hot NumPy method, so we effectively need to implement this as a composition of NumPy methods. And what we can then basically do is run our torch one hot method with a NumPy backend. Because, hopefully this is clear enough, but effectively we do this stitching as we've done before. We're running with a NumPy backend, we're running with a PyTorch front end, and then we can effectively run this method with the NumPy backend. To go into a slightly more complicated example, now let's say we want to convert TensorFlow method cumprod or cumulative product into PyTorch code. And this time the front end is implemented by wrapping two Ivy methods, which are Ivy cumprod and Ivy flip, just so that we can add this extra argument that's available in TensorFlow, which is reverse. So this is the TensorFlow front end implemented as a composition of Ivy methods. Then let's assume we're trying to run this TensorFlow code with a PyTorch backend. These two Ivy methods we used are implemented like this in PyTorch. They might look a bit complicated on first sight, but actually a lot of this is essentially just handling the default arguments and doing string list comprehension based on shapes and so on. This just checks if it's exclusive, which is a method supported by other frameworks but not Torch. So we just do a bit of logic here to do an exclusive cumprod. Here it's about the default axis. So if the axis is not present, we need to essentially explicitly, because for other frameworks you flip all the axes then. For Torch this doesn't happen, so we need to explicitly list all these axes based on the size of the input. So basically these are slightly more involved in the back end. But combined, this means that we can import the TensorFlow front end as TensorFlow. Then we have everything operating exactly as TensorFlow does, set the framework as Torch, and then we can effectively call TensorFlow code with a PyTorch backend. So this is effectively then how you can convert TensorFlow code to PyTorch. Okay, so now I'll just quickly talk about the role of the graph compiler in all of this. So that all might make sense and seem perfectly good, but what if we have code like this? Are we also going to wrap Torch's high-level classes and data loaders and everything else that can be found in the very large Torch module and namespace? And this is not something we do because this becomes a huge growing problem to try to maintain this big front end. And we just want to implement the functional API, which is very stable, very kind of contained and doesn't grow really quickly, and much more stable code. So this is then where the graph compiler comes in, where we can actually take any code, get the graph, which stitches everything together as a composition of the functional ops, and then we could convert this graph, not the whole code with everything in the classes and everything. So in this case, yeah, we can't, as I've said, we can't simply convert it. What we can do in this case is we can first effectively compile whatever graph we've got into this graph compiled representation, and then we can call this to backend method. So we can then take our torch module, can convert it to JAX, for example, and then call our PyTorch module using a JAX backend. And yeah, just a bit more on this. The kind of process basically, would look something like this. So we take a module, we can then convert it to an Ivy module, we then compile the graph, and then we switch the backend. So this is how it's possible using the Ivy graph compiler in the backend to make the conversion just with the functional operations. And then this is just another example here where, so then, for example, in this example, we've, for example, taken a PyTorch module. We're taking a PyTorch module, we're converting it to JAX, and then you can actually then train this new model using a JAX backend, basically. So in this case, we could then train it in Ivy, and then we can also convert it to a Haiku module, for example, and actually then train it using Haiku. So we can take any module from any framework, convert it to any module in any other framework, and then train it with the optimizers specific to that framework, which is, very powerful. So you don't have to then just use Ivy's optimizers and Ivy's pipeline. You can just use Ivy completely as an intermediary and go ahead with whatever framework you want to use. So this is kind of Ivy as a code converter. One thing I would just say on this is that this is in active development. So the framework handler, the Backend API, the Ivy API, and the Ivy compiler this is also in active development, but these three are implemented. The front-end APIs are on our to-do list, but we've verified everything that I've just described on kind of small examples and everything, and been able to convert big networks such as Perceiver.io seamlessly between all of the frameworks with very small kind of rounding errors and stuff, and getting identical results on ImageNet. So this is not yet implemented, but this is something that we've got on our roadmap for the next few months. So I would then, there's a lot more to be said on Ivy as a framework. So far, we've focused very much on the functions, code conversions, and the kind of building block basics that underpin everything else. The Ivy container is a very important class, which I've got a blog post on, but there isn't time to dive into that in this talk, because I also want to make sure I leave time for questions at the end. Also, the Ivy array, there's a blog post on it, but I've skipped for this talk just for time. So I'll now talk a bit about the Stateful API, which actually builds on the Ivy container. So if you have questions, then please ask at the end. Just in a sentence, the Ivy container is basically like a souped-up dict, where it has full recursive methods, which enables you to have this arbitrary container like a dict does, and you can then call all of the Ivy methods recursively on all of the objects. It also supports all the built-ins, so if you have a full structure of network weights and you do addition or minus with the gradients, then it recursively applies this operation to all of the leaf nodes. So this is like a very useful structure that we use for data loading and to represent weights in networks, and almost everywhere behind the scenes in Ivy for the higher level stuff we do. But I'll kind of skip over that for now. I think I just went back instead of forward. So now let's go Stateful API. So the most helpful stateful Ivy class is probably the Ivy.module, which performs a similar function to Torch, NN module, or any of the other modules in the various frameworks. And effectively, this is then how we can create a linear layer, for example, using Ivy module. And hopefully this should be relatively familiar to those of you who are using kind of stateful machine learning frameworks. We can explicitly create the variables. In this case, we have a forward method here, and we initialize things in the constructor. So this is, just what it would look like. Again, because we very much build on a functional foundation, where possible, all methods, even if they're a class, have like a functional equivalent which receives the weights explicitly as input, rather than kind of implicitly implicitly applying the weights, as is done when you're using these stateful layers. So we really try to build up on a fully defined functional API in all cases. And then just to say what it would look like, if you then create a linear layer, print your variables, you would get this to screen, which is a container of the variables. And then you can create a network, much like you can in other frameworks, by creating your layers in the constructor, defining your forward pass logic in a forward method here, and stitching things together. And again, in this case, we can actually, so a point here is that we don't need to explicitly create variables when we're nesting modules. So in this case, we've created our linear. This is like the lowest level in the nest, so we need to explicitly define these modules. But then when we have attributes of another module, which are modules themselves, then when you do this initialization, all of the weights will be implicitly found and determined recursively, and we don't need to have this create variables here, because the only variables we care about and we're using are the ones that are defined in these other submodules anyway, so we can ignore that call in this case. And this is up to an arbitrary depth, so you can nest your modules as deep as you want, and all of the variables will be implicitly found. And we can see here, we didn't explicitly define the variables in this class, but when you print the variables, we have them here, and they were named based on the name of the attribute automatically. And then this is the case whether your submodules are direct attributes themselves, as in this case, whether they are contained within lists, which is itself an attribute. We still get this implicit detection of the variables. This is the case also for a tuple as well, or a dict. And this is also arbitrarily nested. So even if it's a dict of a dict of a dict, all of these are recursively searched and the variables are found. Had to split this because it was a bit big. Also nested lists, as I've just said, so fully recursive. The variables are all still found from your submodules and just nested in the weight structure automatically. And same with the duplicate. So here we have linear 0 is an attribute, linear 1 is an attribute, but both are also contained within this list, which itself is an attribute. So we need to make sure we don't duplicate these variables, because it's one set of variables. So here we don't. Linear 3 is the only one that's bound to the attribute namespace, and the others are kind of only bound inside the list. So we don't have linear 0 and linear 1 here as well. Otherwise, because if they were there would be duplication in the variables here. Not sure why this is 3 and not 2. I guess I took one out. So then a final point is that we can also then call the activation layers as stateful layers or modules as well. So in the previous example, we effectively called relu and sigmoid straight from the functional API, and it wasn't a stateful module at all. It's just this function that's defined in the forward pass. We can also define these as modules as well, and actually then call the module. That works completely fine. You might wonder what's the point in doing this, and the main reason is that it enables you to use Ivy sequential, which again is familiar hopefully with some of you in other frameworks, such as Torch I think has this, where you can basically just like, for any layer that simply takes input and returns output, you can just chain these together, and it accepts modules to keep things simpler. So then you can put your relu and your sigmoid as part of this chain of modules. And again, you still have the same weight structure basically. When you do sequential, all of this implicit determination still works out the box. And then you can then train. Let me just quickly check my notes. So basically then this is then what makes it possible to just train a network in a few lines of code. We have our input, we have a target and a learning rate. We then define some model. Let's say we defined our module to be the fully connected class we defined before. And then, we can define the loss function here, which receives the variables explicitly. We explicitly pass the variables in, and then we need to do execute with gradients and provide the function and the variables with respect to the gradients that we want to compute. So this is a fully functional approach. Again, this is necessary in order to support JAX, for example, which is fully functional, but it's also a much more explicit way of doing coding where all your variables are explicitly passed and returned. Nothing's hidden behind the scenes, which is one of the big benefits of JAX that you can't, when you're debugging, for example, you can really just step through and see every gradient computation and every variable being passed inside and out of functions with no hidden states that make things hard to debug. And we support PyTorch and TensorFlow, which do have stateful variables, just by explicitly passing them still, even if this isn't actually necessary for doing the gradient computation. And then here, I mentioned previously that the Ivy container does fully recursive operations. So model.v here is this container, which is like, as I said, a souped up dict. Gradients is also a container with the same leafs and the same key names. And learning rate here is just a scalar. But it could also be a container if we wanted a more complex optimizer schedule. And then we just do the update here, again, fully recursive and get our new weights or our new variables here. Just a quick point before I'm getting towards the end of my kind of blasting through everything. We also then have initializers. So in the example previously, I explicitly created the variables and explicitly did a random uniform method here to initialize them to be within some range. But actually, it's a lot nicer if we can fully decouple the initialization strategy and the layer implementation itself. So we then have these like glory uniform zeros where you can define your weight initializer in the constructor and then just call your initializer create variables here just to enable you to implement your initialization schemes entirely independently from the layers themselves. And this is just then what glory uniform and zeros look like. Actually, both deriving from, so very short, both deriving from more general initializer classes. But yeah, again, this is quite similar to what's done in other frameworks as well. Recapping the example above, we can see this is how the training looks like. This is the example we just saw. But this is only simple vanilla gradient descent. And what if we want to do something like Adam or Lars or Lam or any of the other more complicated and involved optimization strategies? Well, that's then where the optimizer class comes in, which is the final stateful class I'm going to talk about. And this essentially, again, we have a general base class here. I don't think going into every detail of what Adam does is necessary, but suffice it to say that you can essentially then implement a specific step method for your optimizer. In this case, we initialize these internal variables on the first pass. We again make use of a functional implementation because we want to really build everything up from the ground up. So we want it to be possible for people to write their own classes or just operate entirely with a functional API if they want to. So we always delegate in any class directly to a functional implementation instead, which takes in the variables explicitly. And this is just the state because some optimizers are stateful, such as Adam, which has these two states. And what you can then do is train with your optimizer, define Adam, define the learning rate, define all the other variables if you want, like beta and so on, and then train just with optimizer.step with your variables and your gradients, and it returns the new variables in the full stateful manner. So this is kind of how Ivy itself is a fully fledged machine learning framework. Obviously, earlier I talked about the functional API, how we try to unify everything and how we enable code conversions. And this is what we're focusing on early, but also Ivy is itself a fully fledged machine learning framework which supports all these frameworks simultaneously and is as simple as setting ivy.setFrameworkTorch or ivy.setFrameworkJax, and all of this works out of the box with any of those. Oh, sorry, wrong way. So that is a kind of quick blast through the Stateful API itself. The next thing to say, without diving into them at all, is that there are lots of libraries. So I would encourage you to check out our GitHub and check out links to mechanics, vision, robotics, gym, memory. I'll read them all: builder, models, and ecosystem. Which, yeah, I think the names are clear enough. I won't dive into these now, but please check these out, which are all fully implemented in Ivy and are libraries for doing each of these, for applying Ivy to each of these areas. Before closing off for questions, because there's only kind of 10 minutes or so left, I want to say that we're hiring at the moment. So as Oliver said, we've received pre-seed funding. We're looking to hire a team of interns at the moment to essentially help us on our roadmap and to help us work alongside our AI partners at Google. Also, we're in talks with people at DeepMind and Microsoft and Facebook and a lot of top open source contributors. So we want to hire interns to help us work alongside those, get Ivy into better shape, and start to get unified ML all over the open source landscape is something we're really keen to do. And ask me more questions if you want to know more about the internship opportunities or feel free to send me an email. Finally, I'll just ask, please ask any questions, because I have a tendency to blast through things a little bit. So by all means, if there's things that I could explain better, then I would love to answer your questions. But otherwise, thank you very much for listening. They are not, but they can be made available. What I would say is that they very closely follow the blog series on Medium, almost exactly. So I would say that's the best resource, but I can also add the slides somewhere, or send me an email and I can send them over. So in the short term, there's not, but one thing that we definitely are interested in exploring when we get around to it is actually, once we've managed to create this unification in Python, to have a unified compiler so that we can compile to more efficient runtimes in C++, or maybe have direct bindings to ONNX, for example, which is kind of tackling the unification problem for deployment, whereas we're focusing on training more. And when we kind of branch into those questions, definitely we don't want to limit ourselves just to Python. And the good thing is, with defining a unified API, while that is Python specific at the moment, I think that could translate over, because a lot of it is just semantic, and a lot of the unification is not Python specific. So certainly that's something we want to explore. But in the next 12 months, let's say, then this isn't on the roadmap. Yeah, one other thing then, just as kind of final points, is in terms of what we're doing at the moment. In an ideal world, we would love it if everybody was using Ivy today instead of the other frameworks. But this is obviously something that's is not realistic, and it's also not what we're proposing to the collaborators. So when I just go on to, it's right at the beginning, but the folks we're talking to at various open source repositories, and in an ideal world, we could approach PyTorch Geometric or Cornea or PyTorch Lightning or FastAI or any of these, and basically say, hey, why don't you implement this in Ivy straight away? And this is something that we're not doing, because Ivy is still in relatively early stages, and it's not realistic for repositories which have lots of forks, lots of dependencies further upstream, to kind of fully rely on Ivy at this stage. But so that this is then where the code conversions come in, because actually having got the automatic code conversions working, which is something we're pushing to do in the next few months, we can then provide multi-framework support to any framework without changing hardly any lines of code at all. So effectively, then we can take, just as one example, PyTorch geometric, we'll be able to then give examples showing how you can take any function, any code in PyTorch geometric at all, and in one line of code, convert that into a JAX function or convert that into a TensorFlow function that can sit straight inside your own pipeline and then work out the box. So this gives us a very quick avenue to scale very, very quickly, get lots of people seeing IV, lots of people interacting with it with very little manual implementation overhead. But then our roadmap is that if Ivy enables all of this and gains more traction, gains more users, then Ivy will increasingly be in a position with backing and so on, where it's then able to actually act as the backend framework to open source repositories such as these. And this is what we're hearing from all of these maintainers who would love to use Ivy, aren't quite ready to fully depend on Ivy yet, but would like to think that in a few years that's very possible. And this is then just to kind of clarify why this code conversion is so important, because it also gives Ivy an avenue into this machine learning space without dictating that everybody writes everything in Ivy. It's kind of a stepping stone where we enable code conversions, but long term, if we align closely with the Array API standard as well, then there will be less and less reasons not to use Ivy on day one and implement everything in Ivy from the beginning, because then you have all frameworks supported, you have standardization at the API level, and you have future-proofing to future frameworks. So we're kind of working to increasingly become the obvious choice. But starting with code conversions is an obvious way to get us making an impact on these very popular repositories today, rather than kind of delegating that to the future. What function name to use when the framework have different names? Yeah, okay, that's a great question. So basically we decide, up until now, it's been essentially staying as close to NumPy or the middle ground as possible, but actually we're in the process currently of bringing all of Ivy into alignment with the Consortium for Python Data API standards. They have an Array API which defines what the function name should be, what the argument input should be, and the syntax. And this is, an Array API that's got all of the big players involved to try to bring unification. So this is where we're going to in order to decide what our function should look like. Having said that, these are a subset. So this standard doesn't include all functions. It doesn't include gather and scatter. So for the time being, that is just our best guess, or our kind of trying to find the middle ground that adheres to most frameworks and has the least deviation. But that isn't a scientific process. As more and more functions get integrated into the consortium standard, then we will fully adhere to what they come up with, which again is a collective with lots of players involved. And again, just to say that there is cases when we do still need to extend this functionality, because they just provide the bare minimum requirements that all of these functions should adhere to, but they don't restrict functions from having extended behavior for different input types or passing arrays or floats. Maybe the standard would say it needs to support floats and it needs to do this when you pass these functions in, but it doesn't say you can't do even more things if other things are passed in. So Ivy sometimes will still extend on the standard just so that we can capture all of the backends in the most general way possible, whereas the standard instead is actually doing something a bit different. It's not trying to find the superset, it's trying to essentially find the subset. The future plans and next steps. Basically, so we're hiring a team of interns at the moment. What we're working on, as I said, right now in the very short term is aligning Ivy entirely to the consortium for standards. Then we need to implement the framework-specific front ends. So these here, such that we can enable these automatic code conversions. And then once we've got those working, once we've got code conversions working, then we're going to go through making pull requests and forks and all these open source repositories and getting Ivy, getting Ivy's brand out there, getting more people seeing it, more people using it, and just building a community and trying to solve a hard problem in ML for code conversions. Further down the line, with regards to business model and everything, this is still relatively open. And also something that I guess we can discuss a bit more if you do an internship. But basically, we're trying to just make tools that build on top of this stack even further, to just make everyone's lives easier in companies as well, possibly with paid subscriptions and so on. But for the time being, very much our mandate is to grow the community, provide these conversion tools, standardize the APIs, and make everyone's lives easier in research and in companies, all under an Apache 2 license, open source. Yeah. Another thing I would actually very quickly say is that on the GitHub README, we have a Discord server, which is very active. And I'm probably, of all the media, I'm probably most responsive on that Discord server. So if you direct message me there or message there, then you'll definitely get a response. Otherwise, you also will. But if you want a quick response, the Discord is a good place to go.